Hello students, welcome to Time classes. We are here in this session to discuss one of the most important concept from chemical bonding from class 11th. Before to start the topic, I would like to introduce our YouTube channel Time for IIT JEE NET. For more such videos, do subscribe and stay connected with us. What is molecular orbital theory? According to molecular orbital theory, in molecules, electrons are present in new orbitals called molecular orbitals. In case of atoms, electrons are present in atomic orbitals, but in case of molecules, electrons are present in molecular orbitals. These molecular orbitals are formed by the combination of atomic orbitals of nearly same energies and proper symmetry. The atomic orbitals which are involved in the combination, they must possess same energies and they approach with proper symmetry. Molecular orbitals are associated with the nuclei of all the bonded atoms in a molecule. That is, a molecular orbital is polycentric. But an electron in an atomic orbital is under the influence of the nucleus of only one atom. That is, the atomic orbital is monocentric. If we take the hydrogen atom, it has only one electron and this electron is present in the first orbit. So this electron is under the influence of the nucleus of one hydrogen atom. But if we take a molecule H2, so the two electrons are present in the molecular orbital and that molecular orbital is under the influence of the two hydrogen atoms, the nuclei of the two hydrogen atoms. This molecular orbital is influenced by the nucleus of this hydrogen as well as the nucleus of this hydrogen, second hydrogen atom. So the molecular orbital is called polycentric because it is influenced by the nuclei of all the bonded atoms in the molecule. Whereas the atomic orbital, this is the atomic orbital 1s orbital for hydrogen atom. This atomic orbital is under the influence of only one atom. I hope this is clear. The number of molecular orbitals formed is equal to the number of combining atomic orbitals. And among the new molecular orbitals, half are of lower energy than the combining atoms and the other half are of higher energy than the combining orbitals. So if we take the examples of 1s orbital is combining with another 1s orbital, we get two molecular orbitals, that is sigma 1s and sigma star 1s. The other two molecular orbitals. Similarly, 2s orbital combines with the 2s orbital and it gives rise to two molecular orbitals, that is a sigma 2s and sigma star 2s orbitals. And 2px, 2py, 2pz orbitals of one atom combines with 2px, 2py, 2py and 2pz orbitals of another atom and forming the 6 molecular orbitals. They are forming the 6 molecular orbitals. So these 6 molecular orbitals are sigma 2pz pi 2px is equal to pi 2py, pi star 2px is equal to pi star 2py and sigma star 2pz. And from these molecular orbitals, half of the molecular orbitals are of lower energy and that half orbitals are called the molecular orbitals, bonding molecular orbitals. They are called the bonding molecular orbitals. Bonding molecular orbitals. The remaining half, they are of high energies and they are called anti-bonding molecular orbitals. Anti-bonding molecular orbitals. The anti-bonding molecular orbitals are the star-marked orbitals. For example, this is 1, 2 and 3 here, and in this case sigma star 1s and sigma star 2s. I hope this point is clear. So the number of molecular orbitals formed is equal to number of atomic orbitals involved in the combination process, and half of them are of lower energy, which are called the bonding molecular orbitals, and half of them are having the higher energy than the combining atomic orbitals, and they are called the anti-bonding molecular orbitals. The bonding molecular orbital has lower energy and it is more stable than the corresponding anti-bonding molecular orbital. Like atomic orbitals, molecular orbitals also filled in accordance with the Pauli's exclusion principle, Hund's rule, and Abbo principle. That means the distribution of electrons in various molecular orbitals must follow the three principles. One is Pauli's exclusion principle. So in any orbital, maximum 2 electrons should be present. And Hund's rule, so the degenerate orbitals at least hold 1 electron before pairing. Abbo principle, the electrons are filled in the molecular orbitals in the increasing order of their energies. Let us see the energy level of various molecular orbitals which are determined from spectroscopic data. The order is sigma 1s is less than sigma star 1s, which is less than sigma 2s, less than sigma star 2s, less than sigma 2pz, is equal to pi 2px is equal to pi 2py, less than pi star 2px, which is equal to pi star 2py, is less than sigma star 2pz. This is the order for the molecules of the species which contain more than 14 electrons. More than 14 electrons. Now in this case, the starred mark orbitals, that is a sigma star 1s, sigma star 2s, and pi star 2px, pi star 2py, and sigma star 2pz. These are the anti-bonding molecular orbitals. And we can see one equal sign here. Pi 2px is equal to pi 2py, and pi star 2px is equal to pi star 2py. And in all the cases, we have taken the z-axis as the internuclear axis. That's why we got the sigma 2pz and sigma star 2pz. So the equal sign represents that they are having the same energies. Pi 2px is equal to pi 2py. The energies of the two orbitals are same. So these are called the degenerate orbitals. Degenerate orbitals. Similarly, pi star 2px, pi star 2px is equal to pi star 2py. I hope this point is clear. Now for the small molecules, but the lighter molecules, if this is clear, we can go to the next point. For the small molecules, the lighter elements like lithium 2, beryllium 2, boron 2, C2 and N2. In this case, the above order changes. This is due to the mixing of 2s and 2pz orbitals. And why they mix? Because the energy gap between these two orbitals is very less. The energy gap is very less between these two orbitals and they intermix, and the energy of the sigma 2pz goes above the pi 2px and pi 2py. So the modified order for the lighter elements or for these elements is in the order of, that is sigma 1s is less than sigma star 1s, less than sigma 2s, less than sigma star 2s. Up to this common in both the cases, but in this case here there is a change. Sigma 2pz is going above the pi 2px, which is equal to pi 2py, and the remaining part no change. This is for the elements or the species or for the molecules which contain electrons up to 14, equal to 14 electrons or less than 14 electrons, less than 14 electrons. The next point is about the bond order. The meaning of bond order is the number of covalent bonds present between the two atoms. Number of covalent bonds between the two atoms in a molecule is called the bond order. Number of covalent bonds. For example, if we take the nitrogen molecule N triple bond N, between the two nitrogen atoms we have a triple covalent bond, so the bond order in N2 is equal to 3. Similarly, oxygen, O double bond O, O2 molecule. Here the two bonds are present, so the bond order is 2. But based upon the molecular orbital theory, how to find the bond order? The bond order is defined as it is equal to number of electrons in the bonding orbitals minus number of electrons in the antibonding orbitals divided by 2. Or you can say 1 by 2 into number of electrons in the bonding orbitals minus number of electrons in the antibonding molecular orbitals. Nb is the number of electrons in the bonding molecular orbital. Na is the number of electrons in the antibonding molecular orbital. And if Nb is more than Na, the bond is stable. So we get the positive value here. The bond order cannot be negative. Okay. And the bond order can be 0. It can be fractional value 1.5 or 2.5, or it can be 1, 2, up to 3. In some cases, it may go beyond 3 also. And if the number of electrons in the bonding molecular orbitals is equal to number of electrons in the antibonding orbitals, then the bond doesn't exist. Here the bond order will be 0. In this case, the bond order will be 0. For example, if we take the helium-2 molecule, in this case, generally we know that helium doesn't form any bond because they are inert gases. But if we consider according to molecular orbital theory, helium atomic number is 2. So 2 plus 2, 4 electrons in this molecule. 4 electrons means the electronic configuration is sigma 1s2 and sigma star 1s2. So total number of electrons 4. So 2 in bonding molecular orbital, 2 in antibonding molecular orbital. If you apply the formula also, 1 by 2, 2 minus 2 is equal to 0. So the molecule doesn't exist. If the number of electrons in the bonding orbital is less than the number of electrons in the antibonding orbital, then the bond is unstable. In this condition, the bond becomes unstable. And with increase in the number of bonds between the two atoms, or we can say that with increase in the bond order, the stability of the molecule increases and bond enthalpy also increases, but bond length decreases. Bond order is directly proportional to bond energy, which is directly proportional to stability. So bond order, if it is more, bond enthalpy also will be more, and the molecule is more stable or the species is more stable, but bond length decreases. So with increase in the number of bonds or the bond order, the bond length decreases. I hope this is clear about the bond order. The next concept is the magnetic properties. This is the only concept in the chemical bonding which explains about the magnetic properties of the molecules or the ions. If all the molecular orbitals contain paired electrons, then the molecule is diamagnetic. And if one or more molecular orbitals contain unpaired electrons, means single electron, then the molecule is paramagnetic. We take the example of helium-2 plus ion. In this case, the number of electrons in the helium-2 plus ion, helium-2 means 4 electrons, one positive charge is given, so minus 1, so we have the 3 electrons. 3 electrons means the configuration is the sigma 1s2 and sigma star 1s1. 1 electron is present in the sigma star 1s1, that is the antibonding molecular orbital. So any molecular orbital, if it contains one unpaired electron, then it is paramagnetic. It is paramagnetic. And the magnetic property is measured by taking the formula, that is mu is equal to right here, mu is equal to n into n plus 2 square root of this into Bohr magneton, the unit of magnetic moment. So this is the magnetic moment is equal to n. N is the number of unpaired electrons. Let us see the molecular orbital energy level diagram for the nitrogen molecule. Here the nitrogen molecule is made up of two atoms. Nitrogen configuration is 1s2 and 2s2, 2px1, 2py1 and 2pz1. Second nitrogen also we can write the second nitrogen atom. So When you write the N2 molecule, the electronic configuration of nitrogen molecule is sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2, pi 2px is equal to pi 2py. Here we got the 8 electrons over 2 plus 2, 4, 12 electrons, and sigma 2pz2. So 14 electrons. So first two orbitals not given in this diagram, it is started with the sigma 2s2, sigma 2s2. So you can see this is the sigma 2s2, sigma star 2s2, 2s and 2s combining to form the two molecular orbitals. This is the bonding molecular orbital, that is the sigma 1, sigma 2s, and this one is a sigma star 2s, that is a antibonding molecular orbital. 2px1, 2py1, 2pz1 for one nitrogen atom, and this is for the second nitrogen atom. They are combining to form the 6 molecular orbitals. Pi 2px is equal to pi 2py, sigma 2pz, and here is a pi star 2px which is equal to pi star 2py, and this is a sigma star 2pz. So the molecular orbital electronic configuration is, or energy level diagram is, sigma 2s2, sigma star 2s2, pi 2px2, pi 2py2. These two are the degenerate orbitals. We can see the energy also they have in the same energies here. And then sigma 2pz2. If we want to find the bond order, we can take the bond order is equal to 1 by 2. Number of electrons in the bonding molecular orbitals 1, 2, 3, 4, 5 means 10, minus number of electrons in the antibonding orbitals 1, 2, 2 means 4 is equal to 6 by 2 is equal to 3. So between the two nitrogen atoms, we have a triple covalent bond. I hope this is clear about the nitrogen molecule, and all the molecular orbitals are filled by electrons. There is no unpaired electron in any molecular orbital. So this is a diamagnetic molecule. The next we will go for the oxygen molecule, the molecular orbital energy level diagram for the oxygen molecule. Here the configuration is changing here. Sigma 2pz will come below the pi 2px and pi 2py. Oxygen total number of electrons are 16. So each oxygen atom configuration is 1s2, 2s2, 2p4, 2p4. Similarly, this is one oxygen atom and this is the second oxygen atom. In the middle, we have the oxygen molecule. And when you write the 16 electrons, the configuration is the sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2. And next one is a sigma 2pz2 here, pi 2px2 is equal to pi 2py2. Next one is a pi star 2px1 is equal to pi star 2py1. You check the configuration. 2 plus 2, 4 plus 4, 8. 8 plus 10, 2, 10. 10 plus 4, 14, 15, 16. And this molecule is a paramagnetic. Why? Because the antibonding molecular orbitals are having the single electrons or the unpaired electrons. So this molecule is paramagnetic. By applying the formula, we can calculate the magnetic moment. Properties of oxygen and its ions related to the bond order. So here this is a point where you can get the questions. We can expect the questions in the any competition exam. Some examples we have taken related to the oxygen and its ions. The species are O2, O2 minus and O2 2 minus. In case of oxygen, we do the bond order is equal to 2 and number of unpaired electrons are 2 here. It is a paramagnetic. So in case of O2, the last orbital electron configuration I'm writing sigma 2pz2 pi 2px2 is equal to pi 2py2, and then we got the pi star 2px1 is equal to pi star 2py1. So I have not taken the first 4 orbitals. Now we got the unpaired electrons in the pi star 2px and pi star 2py. So the number of electrons are 2 here, and it is paramagnetic. Next one is a O2 minus. O2 minus means one electron is added. Here one electron is added. So we get the pi star 2px2 and pi star 2py1. Here the bond order, if we calculate, it will get the 1.5. This is 1.5. And the number of unpaired electrons is equal to 1, and it is a paramagnetic. Next one is a O2 minus, means 2 electrons are added. So in O2 minus, the last orbital configuration will be pi star 2px2 and pi star 2py2. You have to put the sign, equal sign. So here the number of unpaired electrons is 0. We don't have any unpaired electron, and the bond order is 1. If we check the number of electrons, 16 electrons for oxygen, 16 electrons. Here 17 electrons, and here it is 18 electrons. So based on the bond order is 2, 1.5 and 1. So here the bond length will decrease if the bond order is more. So O2 is less than O2 minus is less than O2 minus. Similarly, bond strength is directly proportional to bond order. So O2 is more than O2 minus, and it is more than O2 minus. Similarly, we can also consider like O2 2 plus, O2 plus, and O2 minus, O2 2 minus. If we check the number of electrons here, number of electrons, this is a 14 electrons, and here it is a 15 electrons, and this is 16 electrons, and this one is 17 electrons, and here it is a 18 electrons. In case of O2 2 plus, the bond order will be 3. Here the bond order is 2.5. This is the 2 here, and this is the 1.5, and this is 1.0. This is the shortcut method to remember the bond orders. O2 2 plus 2, O2 2 minus. So 3, 2.5, 2, 1.5, 1.0. If we can remember the bond orders, then we can compare the bond length in all the 5 cases. Similarly, bond strength, and also the magnetic moment from the configuration or by knowing the number of unpaired electrons. Similarly, let us consider the properties of nitrogen and its ions related with bond order. Let's consider the 2 cases, N2 and N2 plus. Here the bond order is 3 for N2, and it is diamagnetic. And in case of N2 plus, 1 electron is removed from the pi 2py. So we get only 1 unpaired electron, so it is a paramagnetic. Based upon the bond order, we can find the bond length of N2 is less than N2 plus. Bond length of N2 is less than N2 plus. Bond strength will be directly proportional to the bond order. So N2 bond strength is more than N2 plus. And because in nitrogen there is no unpaired electron, so magnetic moment is 0. So N2 is less than N2 plus. Let us consider some questions from the molecular orbital theory. Which among the following is paramagnetic? Paramagnetic means the molecular orbital must contain at least one unpaired electron. Suppose if it is the lithium 2. Lithium 2, here is a 3 plus 3, 6 electrons. 3 plus 3, 6 electrons. And sigma 1s2, sigma star 1s2, and sigma 2s2. So it is not having unpaired electron. So this is not the answer. Next, B2, if we take boron atomic number is 5. B2 means 10 electrons. The electronic configuration is sigma 1s2, sigma star 1s2, sigma 2s2, and sigma star 2s2, and pi 2px1 is equal to pi 2py1. That means we have the unpaired electrons. So let us put a tick mark on the boron. And in case of fluorine, fluorine is 18 electrons. 18 electrons, and we just did the O2 2 plus O2 2 minus. O2 2 minus. The bond order is this is equal to 1. Bond order is 1, and it is a diamagnetic. 18 electrons. If we write the electron configuration also, we'll get Cn minus carbon is equal to 6 electrons and nitrogen is 7. 1 electron is added. So total is equal to 14 electrons. 14 electrons means it is equal to nitrogen configuration. Is equal to nitrogen configuration. Here the bond order will be coming 3 and the number of unpaired electrons will be 0. The next question is, which of the following pairs has the same bond order? The same bond order means if they are isoelectronic. Isoelectronic means same number of electrons. If the two species have the same number of electrons, then they will be having the same bond order. Now Cn minus and NO plus. If it is the Cn minus, the first case, Cn minus and NO plus. Carbon is 6 plus nitrogen is 7 plus 1 is equal to 14 electrons. NO plus nitrogen is 7, oxygen is 8, 7 plus 8 minus 1. So 14 electrons. So the answer is option A only, but we have to check with the other cases also. Similarly, if we take the He2 plus, we got the 3 electrons here, 3 electrons. C2 is equal to 12 electrons. So it cannot be the answer. Similarly, Cn and NO plus is given. If it is a Cn minus, then it could be the answer. But O2 plus and N2, O2 plus is equal to 15 electrons, N2 is equal to 14 electrons. So isoelectronic species have the same bond order. Let's move to the next question. According to molecular orbital theory, the molecule that contains a double bond consisting of 2 pi bonds is. Here 2 bonds are there, double bonds. Generally in chemical bonding, so far we studied that in a double bond, one is a sigma bond, one is a pi bond. But in this case, the 2 double bonds are consisting of the pi bonds only. Let's take the examples. Boron is given C2, O2 and CO. So if you write the boron configuration, boron molecule, 10 electrons. Sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2, pi 2px1, pi 2py1. So this is the configuration of B2 molecule. In case of C2, after writing all the examples, we can understand this question. C2 is 12 electrons. The electronic configuration of C2 molecule is sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2. Here 8 electrons over. Next one is pi 2px, 2, pi 2py2. So in this case, we have, this is the pi 2px and this is the pi 2py. So these are the bonds. Here these are the bonds. A bond contains the 2 electrons. So here we have the 2 bonds. The total number of electrons are 8 plus 4, 12. And these are made up of the pi orbitals. They are made up of pi orbitals. So it contains the 2 pi bonds. In case of O2, we got this one is sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2, sigma 2pz2, pi 2px 2 is equal to pi 2py2 and pi star 2px1 is equal to pi star 2py1. And in case of CO, carbon is 6 electrons plus oxygen is 8 electrons, total is 14. So we can write this like the nitrogen molecule. And in the nitrogen molecule, we have the triple covalent bond, 1 sigma, 2 pi bonds. In case of C2, we can find pi 2px2 and pi 2py2. So these are the 2 pi bonds in case of C2. I hope the concepts we discussed in this session are clear, and thank you for watching the video.